Hello. Good morning, everyone. Am I audible, please?
Sir,
Yeah.
we
Okay.
can hear.
Good morning, Professor.
Good morning, sir. How are you doing?
Yeah, fine doing. How are you doing?
I'm doing well. You tell me how things are.
Yeah, things are as usual. There is no much changes.
No, keep hearing news that some online exams, some college opening, UGC doing something. So maybe
As of-
you can update the students what is
yeah,
happening.
yeah. Already the contact. I already interacted with these students with other faculty many times.
Oh, okay.
I've already, if they have any clarifications, they can ask me. I will clarify.
Yeah.
Otherwise, as of now, it is only up to 3rd of May. We have to wait.
After that, we don't know what will happen.
No, what will happen? It will extend. As Corona is extending,
Yeah.
lockdown also will extend.
So, students, if you have any questions to ask the principal, sir, Professor Gondaraju, please feel free to ask. Anything you mind, any concern, whatever, the exam, course, anything you feel like, feel free.
Feel free to ask me any clarifications you need regarding the college or the university issues. I will clarify. I can have wonderful online classes out of 1 or 2 minutes.
Yeah.
Adarsh, Aisha Sultana, Aniket. I think they were not unmuted. I will. They can unmute, Alva.
They can unmute themselves and talk. So,
No problem. Okay,
yeah.
okay.
If they need to,
I think
they normally unmute and talk.
yeah. I think they have got all information. They don't have any clarifications, I believe. They already know, and also they may visit the VT website often to see the new notifications.
Yeah,
And,
I'm the only one who don't go to VTU. I know you'll give me all the information.
Arpita,
Guys, speak something,
Aisha Sultana, Adarsh, Ashwini,
or anyone else.
Sushmita, so many are there online.
Yeah, but 65 are there.
Yeah, 65 are.
Yeah.
Yeah. Out of 107 or 108, I believe.
About 140.
114, yeah. 50%.
It will become about 75, 80, sometimes become 90.
Yeah. No, it has reached even up almost near to 100.
Yeah,
it is keep
it has. 100 is the limit. So anyone has any questions, even with respect to internals, anything of that kind? Evaluation.
Any issues of college, exams, internal assessment, EBTU? Gagan, Bhumika, Chaitra?
Maybe CR can raise. Gautam and Saurabh, maybe you can raise and ask.
Yeah, Gautam.
Because you are the CR, you may be able to have a better idea what the students' concerns are.
No doubts as of now, sir. We are cleared with everything.
Okay, good. If everything is fine, I'll request the professor to continue his class.
Okay, thank you, sir.
Thank you, sir. Take care of yourself.
Sure.
All the best.
Thank you. Okay, guys, so let's start. Today we'll discuss multi-stage graph. It is one kind of application for dynamic programming. And a multi-stage graph you can look at as a partition of a graph that you have a source vertex, you have a destination vertex, and there are a number of partitions of vertices such that edges goes from partition I to partition I plus 1. There are no edges from partition I to I plus 2 or partition I plus 3. Only from vertices in one stage, there are vertices to next stage. But there are no vertices cross stage. And there's some kind of problem that fall into this category. And we need to look at when such a graph is there, how do you find a minimum cost or maximum cost? Please note that minimum cost, we know you can always find maximum, you can change the value to negative. So whatever positive minimum be, negative would basically be maximum. Hello? Any questions? So I'll probably give you a layman example. We all probably go to some restaurant to eat. Yes, Kalpita, you have a question? Kalpita, you raise your hand. Any questions?
No answer.
Kalpita, if you have a question, let me know. You're raising your hand. Otherwise, I'll proceed.
Sorry, sir, by mistaken.
Okay, no issues. So let's look at restaurant. We all probably gone to a restaurant, and if you go for a normal formal meal, we basically pick up items from the following. We start with soup and starters, then we go for main course, some curries, we take bread or a rice, what we call chapati, sweets, and finally we end up paying the bill. Now you see that each happens in the stages. First stage we go for a soup, second stage we look at the starter, third stage we choose the curries, then we have to order the bread, then we order the sweets and the mouth fresheners. And so our objective is, given such a case, what is the minimum cost we can have to have our meal? And in each stage we have multiple choices, which will come in a short while. But again, there are constraints. If you have taken something in stage X, other thing depending on what you choose on the stage X will depend upon stage Y. And that is what we'll probably look at. I'll give an example and then we say, look at real life example, how do we go about it? But essentially, having chosen one item in stage 1, there are constraints on what you can choose in the next stage. So let's look at the example in the case. If we look at our first stage is basically soup. We start from getting into a restaurant. First stage is soup, then we choose a starter, then the curries, then either a bread or a rice and sweet. And each stage, assume for simplicity that we take only one item. I know that you may like to order one or two or more curries, but for understanding our problem, we are assuming that in each stage, we will pick only one item and different item at different prices. So let's say soup choices, we have 3, tomato, sorba, vegetarian. If you take tomato soup, you can take both the items in a starter. But if you take vegetarian, you can only take saslik. Sorba, you can take only both of them. Tomato soup, you can only take bhaji. So these are the constraints given to you. Similarly, having taken a starter, there are different choices of curries. And if you take a saslik, you want to take kofta, you can take a dal. If you take a bhaji, you can take a mixed veg, because bhaji is all a mixed veg. And then you can take either rotis or rice or pulao. And then your choices among sweets, what kind of sweets we want. And finally, you end up paying the bill. Now, each item here has a different cost. And given that in each stage, I can pick only one item. I can pick one item from here, maybe one item from here, one item from here, one from here, one from here, and get the total cost. So given such a choice, we would like to know what is the minimum cost and how do we go about finding the minimum cost. And that kind of problem we are basically dealing with minimum multi-stage graph, and that is what we'll look at. So let's look at a simplistic case. Consider the following graph. The graph has 5 stages. Source is always stage 1, destination is the last stage, and then intermediate stages. So this graph has 5 stages: stage 1, stage 2, stage 3, stage 4, and stage 5. And we have different way to go from stage 1 to stage A to B, B to C, C to last one. So what approach we take? Can we take a greedy approach? Will the greedy approach gives me minimum cost? If graph is of this kind, that each stage has only one node, then greedy approach might work. Like you might see, I can take first case, I can take this path cost 2, then I can take cost 1, I can take cost 2, then I can take cost 1 minimum, then I take this cost, and then I take this cost. So this is my minimum cost, and I can find it out. So in this case where each stage has only one node, greedy approach does work. But does it work in general? Let's look at the following graph. The graph has 4 stages. S is the first stage, T is the last stage, 4th stage, and then we stage 2 and stage 3. Now in this case, does my greedy approach work? We took in the previous case, the greedy approach works, but does the greedy approach work in this case? And I would like to answer, if I take a greedy approach, what would the path from S to T would be, minimum cost path, assuming I'm taking greedy approach. Any answers? If I take a greedy approach, what would my shortest path from S to T would be? Kavita, Lokesh, anyone? Nikita? Yeah. If I were to take greedy approach, the shortest path is answer given by
C to F, sir.
Yeah. So S to A, because A is the minimum cost from A to D, and from D I have only one choice. So my total cost becomes 1 plus 5 plus 20, which is 26. But in actually, what is my minimum cost path here? If you look at my minimum cost path is S to C, C to F, F to T, which is 7 plus 3 plus 5, which is 50. So we look at how do we go about. So we know that in this case, my greedy approach does not work. So what should we do to find a minimum cost path in such an example there? So when we know greedy approach doesn't work, what should we do? We look at basically greedy approach is this, best approach is this. So let's look at, there are two approaches we can use. One is called forward approach, other is called backward approach. Forward approach means we're starting from S. From S we need to find shortest path to T. So first we find shortest path from, go to next stage, from A find shortest path, from B find shortest path, from C find shortest path, and then take minimum of this edge plus shortest path from A, this edge to B from shortest path from B, and so on and so forth. So if we're looking at forward approach means go one stage next, and for each vertex in the next stage, assuming we know the shortest path, if we know the shortest path, then I know from shortest path from S would be minimum of S to A plus A to T shortest path, or S to B and B to T shortest path, or S to C, C to T shortest path. So minimum of this, and that is what basically a forward approach is. So let's look at what the shortest path would be. we find shortest path from A to T, and let's say that this shortest path is denoted by D, A comma T, a starting node from A to my destination node T. Similarly, let's say shortest path from B is denoted as D, B comma T, D is the distance, and the shortest path from C is C to T, and that means now my shortest path from S would be minimum of this as 1 plus DAT, then minimum and 3 plus DBT, and then 7 plus DCT. So we look at my shortest path would be first as shortest path from that first as to the destination, second as, third as, and now we need to compute again internally what is DAT, compute DAT, compute DBT, compute DCT using the same approach. So let's look at what is DAT is. DAT would be if you look at minimum of 5 plus D dt, 5 plus D dt, and 10 plus DET. So if you look at DAT is minimum of 5 plus DDT and 10 plus DBT. And that is what you're looking at, 5 plus DDT, this is the 5 cost, and this distance, this cost, and this distance. This is gives me DAT, and we know DDT, if you look at DDT is 20, sorry, and this 5, so 5 plus 25 plus 20 is 25, and 10 plus 14 is 24. So minimum of DAT, my distance is 24. Same way, when I look at DBT, my DBT is minimum of 8 plus DAT, 6 plus DET, 15 plus DFT. When I look at DBT, DBT is minimum of 8 plus DDT and 6 plus DET and 15 plus DCT. So 8 plus D, and we know DDT is 20, so this becomes 8 plus 20, 28. Then 6 plus DBT, DET is 14, so 6 plus 14, and this is 15 plus 5. So get 8 plus 20, 6 plus 14, and the minimum is 20. So we know DBT is 20. And same way we calculate DCT. If you look at DCT, is minimum of this as CE, the cost of 4, plus DBT, and this as CF, the cost of 3, plus DFT, so 4 DET, this cost 4 plus DET, and minimum of CF plus DFT, so you know 4 plus, if this is 4 plus 14 gives me 18, and 3 plus 5 gives me 8, so minimum is 8. So I have my with me now DAT. DAT is 24, so this is 24. DBT is 20, and DCT is 8. So my DST is minimum of 1 plus 24, which is 25, 2 plus 20, 22, 7 plus 8, 15. So 1 plus 24 from here, 3 plus 20 comes from here, and 7 plus 8 comes from here, and this happens to the minimum. So this is the way I approach. Now look at where does dynamic programming get involved here. If you look at, in this case, this DAT computation, or the DDT computation is being used when I compute DAT, so look at DDT is being used here, DDT is being used here, so this is called overlapping subproblem. I'm computing it again. That means I should be able to store it and make use of it. Similarly, if you look at this ET, DET, or sorry, what is called, yeah, DET is being used here, DET is being used here, and DT being used here in 3 times. So again, overlapping subproblem, and we don't have to compute again and again. So if you were to take any divide and conquer and any other approach, we would end up recomputing it. But using dynamic approach, we will basically compute once, store the result of this, and use them, and that is what the dynamic programming is. So this we have done is what we call is forward approach. Backward approach would be another approach, backward approach, that basically means when I need to compute from S to T, I first compute to the last stage, that is S to D, S to E, S to F, and then sum them up. This DSD plus SDT, DSE plus ET, and DSF plus FT. So if I were to compute the cost to the last stage and then find the last stage, this is what we call is backward approach. So we can do this either using a forward approach and backward approach, and both will give the same answer. Using backward approach, my DST would be minimum of DSD plus DDT, DSE, and DSF. So minimum would be DSD, if you look at, plus S cos DT, DSE plus S cos ET, and DSF plus S cos phi t. So DSD plus 20, DSE plus 40, DSF plus 5. We'll compute DSD same way. What my DSD would be, if you look at DSD, is I need to compute minimum cost from A to D. And that means look at from cost DSA plus AD, DSB plus B. And that is what we are looking at. So if we look at my DSD is S to A plus S cost phi, S to A plus S cost phi, S to B plus S cost 8, S to B plus S cost 8. The D is only 2, I just will look at those. And DSA is 1, so 1 plus phi. DSB is 3, 3 plus 8, so this minimum is 6. So DSD is 6. Similarly, we can compute DSE. If you look at DSE, DSE is again DSA, then A to E, DSB, B to E, and DSC, C to E. So DSA is 1 plus 10, DSB is 3 plus 8, 6, and DSC is 7 plus 4. This is what we get. So this 11, 9, 11, minimum is 9, so we know DSC is 9. Similarly, we compute DSC. DSC would be, sorry, you need to compute DSF. And DSF would be S to B, B to F, S to C, C to F. So DSB is 3, 3 plus 15, DSC is 7, 7 plus 3, 10, and this is 10. So we have the, if we look at the S cost, DSD is 6, so this is 6, DSC is 9, this is 9, and DSF is 10, this is 10. So if I take a minimum of 26, 23, and 15, this gives me minimum of 15, and that is my minimum estimate. So using both forward and backward approach, we can approach and solve the problem. So where do you use this? What kind of real life applications? I'll give another example, and then we talk about building the algorithm. Consider that you are a team of 3 students and you need to going to participate. You can play 4 games. All 4 games have to be played. Let's say 4 games are this. Now anyone can play all the 4 games, or you can play none of the games, but at a time only one student can play the game, and the no game can be played by 2 people. These are the constraints, and we look at is something like, let's say, consider you have the projects to be done. We need to allocate different resources. So we need to see which resource giving to which faculty would give the maximum benefit. It's something like this: which course to be given to which faculty be most impactful, your number of people, your number of resources, and then decide which courses to be given to which so that one can get maximum benefit. So as in this game, no game is to played by 2 students. A student can play all the 4 games or may not play any game or play some of the games. And because of playing the game, you get different points. And since all students have different capabilities, they probably get different points playing the games. And so this is how the games marks are awarded. Student 1, if student 1 plays what is called one game, first student plays one game, you get 2 points. If he plays 2 games, gets 5 points. If he plays 3 games, get 7 points. If he plays all the 4 games, get 8 points. Same way, student 2 plays 1 game, get 4 points, and student 2 plays all the 4 games, get 10 points, and student 3 plays 1 game, get 5 points. Now remember here, if student 1 has played 1 game, then student 2 can play 1, 2, or 3 games. It cannot play 4 games because no game can be played by 4 students. If student 1 has played 1 game, student 2 has played 2 games, so 3 games are already played. That means third student can only play 1 game because total of 4 games have to be played, and this has to be clear. So the points here are basically in non-decreasing order, or what we call is increasing order. If you play 1 game, you get certain points. Look at student 3, plays 1 game, get 5 points, plays 2 games, no extra benefit, plays on, still get only 5 points. So these points are cumulative. It's not for second game, but for 2 games together, or this is for 3 games together, something of that kind. Now your objective is, how should you allocate the game among yourself so that you can get maximum points? And that is the problem we look at. And this problem can be easily mapped to what we call as a multi-stage graph. And using our forward and backward approach, we can solve this problem. So let's look at how do we solve it, go about it. What are the different choices? So remember again, these points are cumulative. When P1 plays 2 games, you get 5 points. 5 points are not for second game, but for playing 2 games, and 8 points. So what are the different choices? Let's do it by brute force, and then we look at how to solve about dynamic programming. So in a brute force, my choices could be that P1 does not play any game at all. If P1 does not play any game at all, then P2 can play all the 4 games and P3 plays 0 games. If P2 plays all the 4 games, you get 10 points, and P3 plays no game, 0 points, so point gains are 10. Alternately, P2 can play 3 games, P2 can play 3 games, P2 plays 3 games, you get 8 points, and P3 plays 1 game, you get 5 points, and then total points is 8 plus 5 is 30. Remember, this is 0 because P1 is playing only 0 games. Next possibility is P2 plays only 2 games, P2 plays only 2 games, so you get only 7 points. P3 also plays 2 games, you get 5 points, so total point is 7 plus 5, 12. Or P2 plays only 1 game, gets 4 points, and P3 plays 3 games, which is 6 points, so total point would be 4 plus 6, which is 10. So this is the choice when P1 does not play any game at all. Next possibility could be or yeah, we can say P2 plays all the 0 games and P3 plays all the 4 games, you only get 6 points. Next possibility is P1 plays 1 game, P1 plays 1 game. That means P1 plays 1 game, P1 get 2, you get 2 points, and then P2 can play a maximum 3 games. The total of 4 games to be played. So P2 plays 3 games and P3 plays 0 games. So total point is 2 plus 8, which is 10. Or because P1 has played 1 game, P2 can play 2 games. When P2 plays 2 games, you get 7 points, and P3 has to play 1 game, which is 5 points. So total points would be 2 plus 7 plus 5, because P1 has played 1 game, P2 has played 2 games, and P3 plays 1 game, total 4 games. So it would be 2 plus 7 plus 5, which is 14. Other is P1 plays only 1 game, P2 plays only 1 game. So P2 plays only 1 game. That means P2 only gets 4 points. And P3 plays 2 games, which is 5 points. And P1 has played only 1 game. So total point is 2 plus 4, 2 plus 4 plus 5, which is 11 points. Or lastly, P2 does not play any game at all. P2 does not play any game at all. So P2 plays 0 games. P1 has played 1 game. That means P3 has to play 3 games, which is 6 points. So total point is 2 plus 6, 2 plus 6, which is 8. This is what you get. Similarly, you can work out other choices. Now we say P1 plays 2 games. When P1 plays 2 games, team gets 5 points. Now choice is P2 to play 2 games. If P2 plays 2 games, you get 7 points, and P3 plays 0 games, so point is 5 plus 7, 12. Or P2 plays only 1 game. P2 plays 1 game, you get 5 points. P1 already played 2 games, and P3 plays 1 game, so point is 5 plus 4 plus 5, which is 14 again. Or P2 plays 0 games. P2 plays 0 games. P1 already played 2 games, which is 5 points, and then P3 plays 2 games, which is 5 plus 5 becomes 10. Or third choice is P1 plays 3 games, gets to 7 points. If P1 plays 3 games, P2 can only play either 1 game or 0 game. So P2 plays 1 game, which is 4 points, and P3 plays 0, so it becomes 7 plus 4, which is 11. Or P2 plays 0 games, P2 plays 0 games, and then P3 has to play 1 game, so it becomes 7 plus 5, which is 12. Or last choice is P1 plays all the 4 games, means 8 points, and other play 0 games. So this is what we call this approach. If you do that, this is called brute force. That means try all possible combinations and find whichever is the maximum. We have seen maximum happens to be 14 points. And those 14 points are whichever way you want to look at if you look at the previous cases, so maximum points happens to be 14 points. This is what we looked at. So how do we solve this problem using dynamic programming, using multi-stage graph? So look at we have 4 stages. Stage 1 we start. Stage end is the game, all the 4 games are played. And then we look at player 1 playing some games, player 2 playing some games, and this is player 3, all the 4 games are played. Now this is player 1. So basically you can say start stage, which is S, and then I have end stage, which is my T. Here player 1 starts, so we'll go to stage which is player 1, and second stage player 2, and this is third stage player 3. Now this player 1 can play 0 game, can play 1 game, can play 2 game, can play 3 game, or can play 4 game. Same way, player 2 can play 0 game, 0 game, 1 game, 2 game, 3 game, and 4 game. But if you look at, if player 1 has already played 4 games, then player 2 can play only 0 games. So this is the only possible line. If player 1 has played, let's say, 1 game, if player 1 has played 1 game, then P2 can play either one game, 2 game, or 3 game. So which are indicating total number of games being played. So in this, each vertex, when you look at each of the vertex, it is player number. So stage is player number and total how many games have been played. If here, so when you say 1 game has been played, that means from here I cannot go there because this indicates only 0 games played, but already 1 game is played, so there cannot be an as. But there could be as like this because this indicates 1 game is played. So let me repeat again. We look at the stages, start stage, which is S, my terminating stage T, then my stage 1, which is P1, playing, stage 2, which is P2, and this is last stage where P3. So this P1 indicates total number of vertices in this stage, number of games played total is 0, number of games played, total games played 1, number of total games played 2, number of total game played 3. These are the only possible 5 vertex I can have this stage. Same way, I can have only 5 vertices here. Total games played 0, total game played 1, total game played 2, total game played 3, and total game played 4. So in each stage, I have 5 vertices. Each vertex corresponds to player and total how many games have been played. Then we draw the multi-stage graph, and then we apply forward approach and backward approach to solve this problem. So let's look at how does my graph will get converted. So stage 1, play some game, I will talk about it. So let's look at the graph. Starting stage, vertex 1, 0 means player 1, maximum 0 games have been played. 1, 1 means player 1, maximum 1 game has been played. Be it 1, 2, player 1, maximum 2 games have been played. Similarly, 1, 3, and 1, 4. Now you look at, if player 1 plays no games, that's 0 points. If player 1 plays 1 game played, you get 2 points. If it's played 2 games, you get 5 points. If it's played 3 games, up to 3 games, you get 7 points. If it's played 4 games, you get 8 points. So these are my edge cost, indicating my awards. Now for second stage, indicate player 2, and 0 cards have been played. Similarly, 2, 1 means player 2, and up to 1 game have been played. Player 2, 2 games have been played total. It is not 2 games by the player 2, it is total 2 games played so far. And that's the thing you have to understand. Now look at the edges, what the edges we can draw. From V10 to VT0, that indicates player 1 did not play any game. No game is played by player 1. No game is played by player 2. Other possibility is no game is played by player 1, but player 2 plays 1 game. So this is the edge. Similarly, player 1 plays no game, but player 2 plays 2 games. So you will have an edge here. So look at this. If player 2 plays only 1 game, my award is 4. If player 2 plays 2 games, my award is 7. If player 2 plays 3 games, my award is 8. So my S cost would be 8. The what is S cost 8. And if player 1 plays all the 4 games, my award is 10. So this has V10 to V24 would be having cost of 10. Now, what is the edges from V11 to V20? This indicates 1 game has been played. this indicates 0 gap has been played. That means this edge is not possible at all. So this edge cannot be drawn. So this edge cannot be drawn, but this edge drawn, this indicates player 1 played 1 game. Only 1 game has been played till player 2. That means player 2 did not play any game. That's why this edge cost would be 0 here. Similarly, you have edge V11 to V12. This indicates player 1 played 1 game, player 2 played 1 game, player 2 played 1 game means edge cost is 4, and that's what you'll see basically here, edge cost is 4. Similarly, this edge indicates up to 3 games have been played. That means player 2 played 2 games, player 1 played 1 game, and player played 2 games. My benefit is we basically get 7 points. So this edge V12, V23 would be cost of 7. And similarly, V11 to V24 would be as cost of 3, so 8, and this is what you'll basically see here as cost of 8. Same way, now we can have edges from V1 to V20. We can't have this edge because this indicates 2 game played so far. This indicates 0 game played so far. So this edge is not possible. Same way, this edge is also not possible because this indicates 2 game played so far. This indicates 1 game played so far. So this edge is also not possible. So only edges possible are V12 to V22. That means player 2 played 0 game. Or this edge means player 2 played 1 game. Or player 2 played 2 games. If player 2 played 2 games, you get 4. If player 2 played 2 games, you get 7. And that's why the cost of this edge is 7. And now finally, from this, we can say player 1 plays 3 games. This edge is not possible. Similarly, this edge is also not possible. Further, this edge is not possible either because this indicates 3 game played so far. This indicates only 2 game played so far. This is also not possible. So only as possible is this edge and this edge. This edge indicates player 1 played 3 games. Only 3 games have been played so far. That means player 2 did not play any game. So this edge cost should be 0. And that's what you'll see. This edge cost is 0. And same way, this edge cost would be 4 because this indicates player 2 played only 1 game. So this edge cost is 4. And similarly, we can have the edges from V14 to all places. So if you look at, this is not possible. This is not possible. This is not possible. This is not possible because player 1 played all the 4 games, implies player 2 can play only 0 games. So only 4 games are played. So only as possibles are basically this. And we can't have any other edge. So only edge you'll see from here is V14 to V24. And this edge cost is 0. And now finally we have the T. We have edges from everywhere. This indicates player 3 played all the 4 games. Player 3 played 3 games. Player 3 played 2 games. Player 3 played 1 game. And player 3 played 0 games. Thus, respective about points would be 6, 6, 5, 5, 0. And that is what you will basically see when you talk. Now you see this is a multi-stage graph. We have a start vertex, we have an end vertex, we have 2 intermediate stages, and then you can take a forward approach or a backward approach, and you'll be able to find the answer to solve this problem. So find the maximum awards using forward approach, and you can do also using the backward approach. So if I take a forward approach, you basically look at, forward approach means minimum of 0 to V10 to T. That's what we look at. So maximum of dV10 0 plus V10 to T and 2 plus V11 to T. Similarly 5 plus V12 to T and then 7 plus B13 to T and 8 plus B14 to T. And by cross working out, we can find these values are 13, 2 plus 12, 5 plus 9. This is basically this, and that means 14. So you see there are two solutions available, both giving you max. So that means either I can follow this path or I can follow this path, and both of them give me maximum. So I can, my one path is 5 and 4, 9 and 5, 15. This is one path. And other is from here we can look at the, sorry, and this is one path, 2 plus 7 and plus 5. So they are the two paths we basically get. This gives the maximum path. So dynamic programming gives us all the number of solutions, and that's what we do. Same way we can continue using backward approach. I will not work out. I'll leave you to work out yourself and find the answers for yourself. So this is a graph given in the book. You can look at how to find the, again, maximum cost path. Now look here, we are given the node numbers sequentially 1, 2, 3, 4, 5. So we look, any graph would have k stages, and multi-stage means you have edges from stage 1 to stage 2, stage 2 to stage 3, stage 3 to stage 4, but to never have any edge from stage 2, stage 3 to stage 5. So stage 1, stage 2, 2 stage. So you have only k stages, and basically you look at, in this case, what is involved is we need to look at how to find the minimum cost path, and that basically would mean finding, I can take a forward approach or I can take a backward approach. Forward approach means this plus 2 to 12, 3 plus 3 to 12, this 1 to 4, which is cos 3, and 4 to 12, and 1 to 5, 5 to 12. So we'll look at, define some indications, and so how do we use dynamic approach, and so that we can work on the algorithm. So let's denote the notation called cost ij. Cost ij mean vertex j in the stage I. So cost ij means vertex j in the stage I. So this would be cost 2 comma 5 to the minimum cost. So when I look at the 5, we will say C 2 comma 5 indicates minimum cost from 5 to the end. This would indicate 2 comma 4 indicating minimum cost from 4 to 2, and similarly if you look at this indicates C 3 cost 3 comma 6 indicating stage 3 vertex 6 minimum cost. So cost ij indicates minimum cost from vertex j at the stage I to minimum cost, and that's the notation we use. And Cij would basically indicate the edge cost. So when I use Cij, that indicates cost of the edge from I to j. When I use the word cost ij, this indicates minimum cost from vertex j in stage I to the destination. And using this, we'll probably find our answers. So let's look at how do you find using forward approach. So basically look at, we need to find solutions from each stage. So we have a stage, we have to find in each stage which is the, because here S is chosen, here T is chosen, and our job is find one vertex in this stage, find one vertex in this stage, and one vertex in this stage. That means in k minus 2 stages, we need to make decisions. Which are the two vertices, which are the vertices in each of the k minus 2 stages, leaving the last one and the first one, last one and the first one. In each of these stages, find one vertex which is on the minimum cost path, and that is what would say we need to make k minus 2 decisions. And that means we look at the decision each stage, find a vertex and proceed about it, and that's the solution we basically get. So look at the solution would be, Let's say consider stage I, cost ij. So for cost 2, minimum would be h cost 2 to 6 plus, so if you look at here, cost 2 comma 2 means stage 2 vertex 2 would be min of 4 plus cost 3 comma 6, meaning look at the edge cost from this node j to vertex and from the vertex in the next stage the minimum cost. So take the minimum of, so this will minimum of this plus this plus this plus this, and that is what we are basically saying. We're looking at our cost, and this how we'll proceed. So we'll work out the example and then you see. We know this for the last stage, which is k minus 1th stage, minimum cost is the edge cost, if the edge exists. So let's look at, for the last stage, my k minus 1 stage cost is same as edge cost, and that's what we are showing here. So now look at, first find what is the cost of C36, and we keep figuring it out, and we do that. So we do for each vertex and figure out. So look at my cost 36. Cost 36 means this is my stage 1. If you look at, this is my stage 1, this is my stage 2, stage 3, stage 4, and stage 5. Or you can, it is given here. Stage 1, stage 2, stage 3, stage 4, and stage 5. In stage 3, vertex 6, what's the minimum cost? So stage 3, vertex 6, minimum cost is this edge cost 6 plus C9 cost 9, 4 comma 9. So stage 4, vertex 9. So edge cost 6 plus stage 4, vertex 9 minimum cost, and this edge cost 5, which is C6 comma 10, plus stage 4, vertex 10, stage, this should be, sorry, this is not cost 5, this should be stage 4. Sorry, typo there. And this basically means it becomes 6 plus 4 is 10, 5 plus 2 7. So my minimum cost C3 comma 6 becomes 7. Similarly, compute C3 comma 7. Cost 3 comma 7 would be 4 plus 4, 3 plus 2, and this again, sorry, again typo there, this should be 4 again. Cost 4 comma 10 and not 5. Typo there, so let me correct this. Similarly, compute cost 3 comma 8. 3 comma 8 means stage 3, vertex 8. This indicates 5 plus 2 and 6 plus 5, basically cost 6 plus 4 comma 10 and 6 plus cost 4 comma 11. So this is, if you look at, sorry, here, this should be not 6, this should be 5 plus 4 comma 10, and so this is a typo there again, 5 plus 4 comma 10 and 6 plus this, so this should be 5 plus 2, which is 7. Answer is right, that taken it wrongly here. So I got cost of 6, cost 3 comma 6, cost of 3 comma 7, cost of 3 comma 8. Same way we find out the cost of, now cost of 2 comma 2, cost of 2 comma 3, cost of 2 comma 4, and cost of 2 comma 5. We know from this is what we already got from previous calculations. Now we have to find cost 2 comma 2. Cost 2 comma 2 means minimum cost from this, and this is 4 plus cost of 3 comma 6 and 2 plus cost of 3 comma 7 and 1 plus cost of 3 comma 8. So 4 plus cost 3 comma 6, 2 plus cost 3 comma 7 and 1 plus cost 3 comma 8. This happens to be 7. Same way we find cost of 2 comma 3, cost of 2 comma 3. This is cost of 2 comma 3, which is 2 plus 3 comma 6, 7 plus cos 7 comma cos 3 comma 7, only 2 edges. This gives me 9. Same way I find cost of 2 comma 4. This is stage 2. When I say cos 2 comma 4 means stage 2. Vertex number 4, there only one edge, that means 11 plus cost of 3 comma 8. 11 plus 3 comma 8, which is 18. And same way I find cost of 2 comma 5. Cost of 2 comma 5 is as cost 11 plus cost of 3 comma 7, 8 plus cost of 3 comma 8. This is what we look at 15. So now we look at, we have all the cost from 2 comma 2, 2 comma 3, 2 comma 4, and now my minimum cost 1 to t would be 9 plus cost 2 comma 2, 7 plus cost 2 comma 3, 3 plus cost 2 comma 4, and that's how I'll basically find cost 1 comma 1 is this, 9 plus cost 2 comma 2, 7 plus cost 2 comma 3, 3 plus cost 2 comma 4, and 2 plus cost 2 comma 5. This happened to be 16, and this is how you find the minimum cost. You can take the same way doing backward approach, and same thing will work. So if we look at the algorithm basically is, in this case, previous case graph, even though we are saying all the time cost of 3 comma 6, this 3 is indicated only to indicate the stage. But since vertex are unique, vertex are uniquely numbered, I can basically say cost of 6 means minimum cost from vertex 6, minimum cost from vertex 8. When I say cost of 3 comma 7 or 3 comma 8, just to help you understand that which stage we are in. But in reality, when you do computation, I can just say cost 8 because each vertex is unique. And that is what we do in the algorithm. You write the algorithm there. Sorry. So Cij is the as cost, and cost I is minimum cost from the node I, and Dj indicates successor. So look at, we starting from backwards n minus 1 last. So this was my T point, this is my S point. We're starting from stage here, stage here, stage here. For each vertex here, compute the cost. So starting from each vertex here, keep going till first one and compute minimum cost for each vertex. And how do you compute the minimum cost? We know that cost of minimum vertex is j to the r. So if this is my vertex in this stage, the cost of this is my j and this is my r. So this is my j. So this will be as cost j comma r plus cost of r to the node. And this is essentially what we are saying. You find the minimum, update the destination from this, and then basically find the what is called minimum path cost, and they will basically give me. I find the path. So Pj basically give me path. I look at minimum cost from here and find the path, and this is my forward approach. Same way, backward approach, you can look at reversely. I'm going to skip over it. You can go through. There are other examples there for you to understand. This from OpenCourseware MIT. They basically say consider 3 projects. Each project requires certain resources. If we allocate resource 1 to project 0, we get 6 benefit. If you allocate all the 4 resources to project 0, we get 10 benefit. So there are total 4 resources available, 3 projects. You need to optimally allocate the resources, and objective is which resource should be allocated to which project so that we can get maximum benefit. And same way, like look at the game playing problem, we can create the vertices. This indicates stage 1, that is project 1. total number of resources allocated. V11 means project 1, total number of resources allocated. This indicates stage 1, total 4 resources allocated. This is project 2, total resources allocated 0. Project 2, total resources allocated so far, and this means all the 4 resources allocated. So draw the edge based on the table given to you here. If you draw the edge given the table from here, you would basically see the graph, and then you can, very similar to what we had done, and then you basically use the forward approach or a backward approach. And remember, every time once we compute minimum cost of, let's say, this node or this node, we're going to store it and use it. That's what we have seen here. If we look at previously in our graph, cost 3,8, we compute once, store it, and that's the benefit of dynamic programming. So essentially, this exercise given in the book, work it out yourself, solve the problem using forward approach and backward approach, and that will help you a lot. So in summary, we basically look at multi-stage graph. We do forward approach, means from source, go to the first node and find minimum cost from that. Second node, find minimum cost from that. This is a forward approach. And backward approach is go to the last node, find the minimum cost to the last node plus the minimum cost to the node in the last stage, and this is the backward approach. So we can do forward approach or backward approach, and based on that, we find the solution. Sorry guys, so I think I overshot it. Thank you. I didn't see the notice. I'm done with. Thank you. If any question, please raise me. I'm done.